dots and multiply them together, I will get a positive number no matter what. Sorry. Um, where for the red dots, I do not get a positive value because one of the variables is negative and the other is positive. And when I multiply those two z-scores, a positive 1 times a negative 1, I get a negative number. And the same thing down in the lower right corner. I get negative numbers. So it turns out that this correlation sort of takes all of those possible values. So take each dot in this data set, compute the zx, which is the z-score for the x variable, the height, compute the zy, which computes the weight of that person, and multiply them together, and do that for every point in here. Add those all up, and then divide by n minus 1. It turns out that that will give you, guaranteed, a number between minus 1 and plus 1. And it will give you the correlation of this data set. So I want to talk a little bit about what can go wrong in terms of correlations. First of all, the variables, the two variables that I'm taking the correlation of, must be quantitative. It would be silly to take the correlation between something in your zip code, because your zip code is not numeric, is not quantitative. And if I don't have a quantitative variable, I cannot take a correlation. Okay, it doesn't make sense. Just like the rule that the association does not change if they happen to change the x and the y, the correlation will not change either, because the strength and the direction don't change. Remember, that's all correlation does, is gives me a quantitative value of the correlation, the strength and association, strength and direction of the association. So the correlation between height and weight is the same as the correlation between weight and height. It doesn't matter which order they come in. It doesn't matter which axis they're put on even. Okay. And then finally, just some terminology. Correlation is not a coefficient, and it has no units. You should not say something like, oh, the correlation of 0.7 was 0.733 pounds per inch. That's ridiculous. Correlation, the way it's computed, has no units. And so having any units whatsoever, you could say, in this case, the correlation is 0.733, full stop. That's all you need to say. Now, I want to caution that when I'm computing correlation, the first thing we need to do is make a picture. Make a picture, make a picture, make a picture. Because it turns out that certain very obvious things can go wrong. If I look at the picture, it's obvious that it's going wrong or right. So, nonlinearity. If I do not have a linear relationship, I can compute just fine. I can compute a correlation. But what will that computation involve? And the answer is exactly like I did before. I will divide up at the point of the intersection of these two lines is going to be the mean point, where it has the mean of the x and the mean of the y, okay, established. And that divides up the chart into four quadrants. And then I will color the points depending on what quadrant they're in. So you see the greens up here and the greens down here, just like the other class, where I have the reds here and the reds here, because one variable is above our average and the other is below, or vice versa. And so I see that I get a correlation, and by the way, I could compute a correlation out of this. I could just stick it in the computer and run with it. And in fact, the computer will tell me, oh, it's got a correlation of negative 0.34, and that, depending on the situation, might be very interesting to somebody. But the correlation is all wrong, because you wouldn't call this a weak association, would you? A 0.34 is not a very strong association. So something is going wrong, and the answer is it's because it's nonlinear. You get this bend through this, and you get a lot of offsetting things, because you got the reds and the greens up here competing and the reds and the greens down here competing, and it just happens to be a very small correlation. just to be clear, I shouldn't have computed a correlation at all for this picture. The other thing that can mess up the computation of the correlation are outliers. And I like the example, what I call the clown example, where we've made a scatter plot now between a shoe size and IQ. And you can see that I have a cloud of points right here. And if I just look at those, you'd say, there's no association. And so the correlation would be near zero. But because of various things, I've included in here a bozo, the genius clown. So this fellow who has very large shoes and a very high IQ. And if you think about what will happen when I compute the correlations, I will compute the average shoe size, but because of bozo's size, 30 shoes, the average will be pulled out, right? That'll be an outlier that'll pull out the average shoe size. And the IQ will also be pulled up. The average IQ will be pulled up. And so when all is said and done, I'll have more of, in some sense, the green dots when I compute my correlation than I have red dots. And that will mean that the correlation will be actually positive. Even though really, other than bozo, there is no association between shoe size and IQ. And in fact, consider what happened if I compute the correlation without that bozo the clown. The average will be right down the middle of this cloud of points in terms of shoe size. The average IQ will be right down the middle, and so I will get the 4 sections, which will be basically balanced. I name these 2 slides both where I have problems with the correlation computation, make a picture, because both of them are very obvious if I made a picture. The nonlinearity of the data as well as the outliers of the data will show up, if I make the picture. But sometimes people, this is the caution, don't do this. Sometimes people compute a correlation without ever looking at the scatter plot, and that's silly. That's not, that can be, you could be computing nonsense because you haven't checked for these possibilities. The correlation, by the way, you could set it up to be 0.5 if you wanted to. Finally, to finish, correlation does not imply causation, just like association doesn't imply causation. Here's a plot of a bunch of cities and the number of storks they have that live in that city and the human population. And you can see that there is a positive association. And so someone might say, well, I've got this correlation. All right, I've got a correlation that's positive and large. And so there must be, there's a very tight connection between those two, and therefore the storks are actually causing the human population. That can't be the case, right? We all know that the storks don't have anything to do with how the human population is affected. The storks don't cause more babies, right? So what's going on here? Well, it turns out that the reverse is actually happening. That there are lots of people that live in a particular area, and the storks prefer to nest in chimneys, this species of stork, and so there are lots of chimneys for the storks to nest, and so therefore there are lots of storks. Okay, so it turns out that when I do a plot, find a correlation that's either very close to +1 or very close to -1, I cannot jump to the conclusion that these things are both, that there's some cause and effect here. Okay, there's always the possibility that there's a lurking variable, right? A lurking variable might be out there that really describes the cause. to describe the association I'm seeing. Okay, and just to be clear, you want to make sure to avoid causal language, things that kind of in the way you're saying things imply there's a cause. For example, I might look at the salaries and productivity in a particular company and discover that raising salaries and productivity go together, right? Higher salaries and I mean goes with higher productivity. It would be wrong to say, well, the raising salaries are the thing that are causing the increase in productivity. That's not correct. Uh, um, a better way to say that would be there is employees with higher salaries tend to be more productive. It's not that has less of an emphasis on the fact that the salaries are the thing that are causing the productivity to go up. That's not the case. In fact, you can imagine that actually maybe it's the other way around. It's a very productive employee is going to get raises over the time at the company and therefore will be paid better. Um, I compute a correlation. I get a negative 0.99. And I say, oh, look, that proves in between how much red wine you drink and cholesterol. This proves that drinking more red wine lowers your cholesterol. Right? So there's going to be a negative association here. Saying it that way is incorrect. You may not know that. You may not. That may not be the case. So we have to be careful about the way we phrase it. A better way to phrase it is there is a strong negative association between red wine consumption and cholesterol level. That leaves the cause and effect open. It may be that the red wine is causing the lower cholesterol, but it could just be other things. You like. You eat more. The people who like steak drink a lot more red wine because that's what pairs nicely with a good steak. And actually eating steak lowers your cholesterol. Who knows, right? That may be a lurking variable. So we need to phrase it correctly to indicate that. Here's another one. A child that has two educated parents will graduate from college. Saying it that way is implying that the education of the parents causes the child to go to college and graduate. But really, we've got to be more careful. It might be something else. There might be a lurking variable. So we really should say something along the lines that children whose parents are educated are more likely to graduate from college. That does not imply the causation as the bad sentence does. And so finally, we get to one of my favorite cartoons, XKCD. It's a fun cartoon that has lots of statistics jokes in it, and so I love this cartoon that the fellow drew a couple of years ago, and I'll just let you read it.